All right, 5-4, starting with a couple bell ringers. This first one should be very quick and easy. So, and honestly, I would say if you haven't already gotten out a whiteboard, you probably don't even have to. This is probably something that you could just sort of think about mentally and check yourself on. So this first one's just asking for a degree and leading coefficient. You should be able to look at that and tell in your mind what the degree and leading coefficient are. In this case, the degree is 5, and leading coefficient would be -4. Right, so hopefully you got that easily. And then this other one might take you a second to think. Describe the end behavior of the graph of function f of x equals -x squared plus 4. Now this is a little bit different from the ones we talked about in the lesson, obviously, because I'm not giving you a graph. But the point of this is you should, hopefully from last chapter, be able to look at that and imagine what the graph would look like. I'm not asking you for how many zeros it has. I'm not asking you if it's even or odd, although that should be easy. This is obviously even since its degree is 2. But think about what this would look like. So what it should look like, after you think about it for a second, the x squared tells me it's a parabola. The negative flips that parabola upside down, so it's opening downward. So the end behavior would be as x approaches infinity, y approaches -infinity, and as x approaches -infinity, y approaches -infinity, right? It would look something like that. So whether you're on the right side or the left side of the graph, your y value is still going down. Now, I didn't draw that super accurately because this +4 tells me the y-intercept is 4, if you remember from last chapter, but just a rough sketch so you can sort of visualize what's going on there. All right, so moving on. So talking about different ways to graph polynomial functions. So this is one way. This is kind of like a lot of you guys did last chapter, which is use your calculator, type the function in, and then go to the table to see some values that you can graph. So they've given us a table here, so we're just going to graph those. So -4, 5, 1, 2, 3, 4, 1, 2, 3, 4, 5 should be there. -3, -4, 1, 2, 3, 4. -2, -3. -1, 2. 0, 5, 3, 4, 5. 1, 0. And 2, -19 is obviously not going to fit on this graph, so I'm just not going to do it. But that shows us right here what's going on. Now you can obviously type this in your y equals, hit graph, and you'll get a good idea what this graph looks like. But I should be able to look at this table and also consider the degree of this thing and be able to tell what's going on. So since it's degree 3, that's odd. So that tells me that one side of the graph is going up to positive infinity, one side's going down to -infinity. They have to go in opposite directions. And if I look at the way that the points are here and the order in which I drew them, and if I consider this end part, 2, -19, going from 1, 0 to that point, it sure sounds like it's approaching -infinity, which means the left side must have started from positive infinity. So if I connect these points, it should look something like this. Right? Now the whole point of this is it's just a sketch. This is not incredibly accurate. Now, I'm not saying that I shouldn't try to go through all the points and make a nice smooth curve, but my point is that like this point right here isn't necessarily what we call a relative minimum, which we're going to talk about. But that's the best guess I have based on only having these points graphed. So this should be your answer for the first one here. So you notice as we look here, that point that we graphed wasn't actually what we call a relative minimum. There are points lower than it right in that area. But that was the best we had for the points we were given. All right, so looking at this one, which graph is the graph of f of x equals x cubed plus 2x squared plus 1? So you should be thinking about different things. The first thing that's hopefully jumping out at you is that two of these look like they're odd, and two of these look like they're even. And if we look at the polynomial we were given, it's of an odd degree, right? It's of degree 3. So you should be able to eliminate two options right now, which would be B and D. Those both look even. So it's either A or C, right? So what you might want to do is use your calculator. You could just type that in, go to your graph, and see which one it is for sure. But one thing that you'll learn is if your leading coefficient is positive for an odd degree function, then it approaches infinity on the right side of your graph, which is what C does. And that makes sense. If you substitute a positive number in for x, the more positive the number is that you're substituting in for x, the higher the number is that you're going to get back out, right? If this started out with a negative, then substituting in a high number for x would give you a high negative number back out for y. That's not what we see here, so the answer is C. All right, location principle. All right, so this basically means if we have one point that we're looking at that is below the x-axis and the next point on our table is above the x-axis, then we must have crossed the x-axis somewhere in the middle. In other words, we must have a solution somewhere in the middle of those 2 points. And that's because of what we call continuity. The graph doesn't just jump from one point to the next. It's connected by a nice smooth curve. So somewhere in between those 2 points, you must cross the x-axis. So looking at this, if we relate this to a table, determine consecutive values of x between which each real zero of the function, blah, 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 is located. Then draw the graph. So if we're looking at this table, and you're seeing all these change in signs over here to the right of the table, what they're talking about is from 9 to -1, we went from a positive number to a negative number. Then we went from -1 to +1, another change in signs. Then +1 to -3, that's another change in signs. -3 went to -7 next. That didn't change signs. Those are both negative, but then -7 changed to -19. That's a change in signs. So if we would graph these, the first one would be above the x-axis, second one's below, third one's above, fourth one's below, fifth one's also below, because like we said, there's not a change in signs there, and then the last one would be above, so there is a change in signs there. Right? And like this part says right here, make a table of values. Since f of x is a 4th degree polynomial function, it will have 0, 2, or 4 real zeros. So you should be focusing on your degree to help you determine how many zeros you're looking for. Since this is an even degree function, we're going to expect to see an even number of real zeros. The only exception to that rule is if we have one of those situations where, I'll sketch it over here for you so you remember what I'm talking about. Let's say I have a parabola that barely just glances off the x-axis. That might only have one solution, even though it's an even function. So just keep that in mind. But in this case, the way that you could write your answer to this is you could say between, just as sort of a headliner so you don't have to write that word a bunch of times. And you're going to see, you're going to say between x equals -2 and x equals -1, because that's where the first change in signs took place. And then the next change in signs took place between x equals -1 and x equals 0, so you do have a little bit of overlap there, just so you don't get confused. Then the next change in signs was right there, between x equals 0 and x equals 1, right? And then finally between x equals 2 and x equals 3. So I have 4 lines there which corresponds to the 4 different times we saw a change in signs over there. So your answer to this is actually that whole set of between values right there. That's all your consecutive values of x between which a real 0 is located. So they wrote it like that. I think that's a little bit harder to read compared to the way we did, so write it like that. All right, so next up, you can pull up a table on your calculator if you want to, get some x values here. I'll let you do that. I'm not going to go through this one since I already did the last one. So I'll pause, or you can pause the video and then check yourself in a second. So hit pause now, type it in your calculator. All right, if you're checking back in, should have gotten those zeros. Notice there's 3, and the degree of the function was also 3. So the important thing is not that they're the exact same number. I just want to emphasize that. It's just that they're both odd. That's really what you're more so focusing on. All right, so now they want us to graph this. Estimate the x-coordinates at which the relative maxima and relative minima occur. Right? So I typed this into a calculator and I'm looking at it now. I'm seeing the points -1, 1, 0, 1, 2, 3, 4, 5, 1, 3, 2, 1, 3, 5, and everything else is not really going to fit on the graph. I also want to focus, so that I know how to draw my curve here, I want to focus on, if I go back to -2, so hopefully you're following me on your calculator here, where x equals -2, y is -15. So that didn't fit on my graph, which is why I didn't graph it. But keep in mind that's getting more and more negative, especially if you scroll up on your calculator. Those y values are getting pretty negative pretty fast. So that tells me that y is approaching negative infinity on the left side of my graph. If I look at what happens after this last point that we were able to fit on our graph, 3, 5, the x values get higher and higher quickly. They're approaching positive infinity. So that, combined with the fact that it's a degree 3 function, so it's odd, tells me that my sketch on this, and I'm going to start over because that was pretty bad right there. My sketch on this is going to look something like that. Just going to thicken that so it looks a little bit better. Okay, we'll take it. So it's going to look something like that. That looks pretty good. It looks odd. The leading coefficient, again, is positive, so it's like that example we had a few slides ago. On the left side's negative infinity, right side's positive infinity in terms of your y, so that matches up well. Everything's looking pretty good. Estimate the x-coordinates at which the relative maxima and relative minima occur. So if I just estimate that based on what I'm seeing on my graph, it's looking like I have a relative maximum right there. So maximum and minimum, I think you know what that means. Maximum means the high, minimum means the low. When we're talking about relative, that means relative to the other points around it, it is the highest, or it is the lowest. Not for the entire graph, just for the points around it. So that point right there that I've circled in pink would be a maximum. So at least in terms of my estimation, I would say max at 0, 5. And then for the same reason, I would say min at 2, 1. That's a relative minimum. The rest of the points around that particular point are all higher than it. And then what you can do, and it's looking pretty good as I hit graph on the calculator, but hit second trace, so you're going back to your calculate menu, just like we did last chapter when we were trying to find zeros. But if you look at numbers 3 and 4 on that menu, you're seeing minimum and maximum. So click minimum, for example, and then just like last chapter, slide over to where you think the minimum is, do a left bound, so go a couple left, right bound's a couple right, and then guess is right where you think this thing is. And my calculator is telling me minimum 2.000009, y equals 1. Keep in mind that if you have that many zeros, if it's that close to 2, your calculator is really trying to tell you that the x value there is 2. So that matches up with what we had. We said minimum at 2, 1. And if I calculate the maximum the same way really quickly, doing a left bound, right bound, guess, it's telling me exactly 0, 5. Now, depending on which left bound, right bound, and guess you choose, your calculator might not have given those exact numbers as mine did. So just keep that in mind, but you still should be able to see that those were the correct maximum and minimum values. Even if it said, instead of 0, 5, maybe yours said 0 and then y equals 4.9999999. You should know that's 5. All right. This will be another one. If you want to try it as a practice problem, you can. I'm not going to talk through it because I don't want to make this video too long. So pause if you want to try it. And the answers are right there. Next up, real world example. So rainfall in inches per month in a Midwestern town during a 7-month period is modeled by the function R of M equals all that stuff, where M is the number of months after March 1st. Graph the equation. So go into your y equals. Obviously we're not going to use m's when we type this in, right? We're going to use x's. So I am typing this in right now. And I'm going to go over to my table. Now, these are not going to be the nicest numbers, right? I'm looking at a lot of decimals here, but good news is I can estimate on this graph, and I should be able to get a good idea of what this graph looks like. So I'm going to start at the origin, where x equals 0, I should say. So 0, 3.23 I'm seeing on my graph. So that would be roughly there. 1, 3.73, so that's a little bit higher. 2, 3.93, a little bit higher still. 3, 3.89, roughly the same spot, slightly lower. 4, 3.67, so it's about 2/3 of the way between 3 and 4. 5, 3.33, so about 1/3 of the way up. 6, 2.93, maybe there. 7, 2.53. 8, 2.19. 9, 1.97. And 10, 1.93. So looking something like that, if I hit graph on this, and it's tracing this out, looks pretty close to what I have up here. So I could connect these as such. And at least for part A, that's all it told me to do, so hopefully you're able to do that. That's what they got there. Let's see if there's a follow-up. Yeah, describe the turning points of the graph and its end behavior. So turning points is talking about where do we really have a relative maximum or a relative minimum? In other words, where's the graph changing from going up to going back down, or from going down to sloping back up? So where is that happening? Well, it looks like, if I go back to the table just to be careful, it looks like at the point 2.93. That's my relative maximum. So that's right there. So I'm going to say, maybe I'll just say relative max at 2, 3.93. And that's the only turning point we're seeing. We don't have any relative minimum here. And sometimes you'll have more than one relative max, sometimes you'll have more than one relative min, sometimes you'll have none of either. It's whatever you're seeing. There's nothing that's going to be consistent every time. End behavior, all I can say on this one, x is never really approaching negative infinity here because it never goes to the left of 0. I never have a negative x value. So all I can say is as so if we compare it to what we already wrote, it would say as x approaches infinity, y approaches negative infinity. But I'm thinking we want to phrase this in terms of the real world example. So yeah, they just said it, R of m decreases as m increases. And they also said there's a relative maximum at month 2, which would be May. That would be your maximum rainfall, would I guess be around May 1st. So I'm not too concerned with how you phrase those things, more concerned with if you're seeing them. Let me try to finish these last ones very quickly. What trends in the amount of rainfall received by the town does the graph suggest? All right, what trends do we see? I would say maybe the most rainfall tends to be in the spring or early summer, and it sort of declines as the year goes on. So they said the rainfall increased the first 2 months, then decreased. Again, I'm not going to be super specific on that. And then, is it reasonable to assume the trend will continue indefinitely? So think about that for a question before you look at the answer, or before I give you the answer here. Indefinitely means basically forever, for the foreseeable future. So do I have any reason to assume that the trend will change? Well, is it reasonable to assume that? No. Why is it not reasonable to assume that? Well, this is going to go down until when? Well, until that following winter ends and starts going into spring. Then we're probably going to get some rain again. It's not like the rainfall continuously goes down forever because a new year starts. So, no, that's not reasonable. All right, so if you want to switch over to the huddle, looking at the 5-4 huddle, try those 3, do parts A, B, and C, pause the video, work with your team, and then check back in. All right, so part A on these 3 is just graphing. You should be able to do that yourself. There's not really a way for me to communicate that to you through the audio here. Obviously, I could put the graph up, but I think you should be able to do that using your calculators. So I won't talk about part A. Part B, you should have said between x equals -1 and x equals 0, x equals 0 and x equals 1, and x equals 2 and x equals 3. That's where you have your zeros. Part C, you're going to have a max at x equals 0 and a min at x equals 2. Number 2, part B, all you have is between x equals -1 and x equals 0. So there's an example one that's degree 3, but all we have is that 1, 0. Again, 1, 0, if I have 1, 0, 1 is an odd number. And degree 3 is also odd, so that makes sense. And then we have a max at x equals -2 and a min at x equals -1. Also, I know in the lesson I gave those as ordered pairs. You can either give them as ordered pairs. I would prefer it that way, or you could just state the x value. Really doesn't matter how you write that. But again, I would prefer it as an ordered pair. I just don't have them down on my paper here to tell you quickly what they are, but hopefully you did it that way. And then number 3, part B, between x equals -2 and x equals -1, and x equals 1 and x equals 2. So there's 2 of them. The degree there is 4. So again, not the same number, but both even, so that sounds good. And then part C, we have a min at x equals -1, a max at x equals 0, and a min at x equals 1. So 2 minimums on that one, and only 1 maximum.